Hi, I'm Bob. Welcome back to 5 Minute Econometrics. If the error term in a model has a non-constant variance, we use the weighted least squares or the feasible generalized least squares estimation methods to account for the heteroskedasticity. WLS or FGLS estimators are consistent and efficient estimators of the population parameters. This conclusion is based on the correct specification of the heteroskedasticity structure. In other words, the heteroskedasticity function must be correctly assumed or specified before we can obtain a consistent and efficient WLS or FGLS estimator. We have tried three specifications of the heteroskedasticity function hx, which equals x squared, or the flexible exponential function. However, it is not guaranteed to be the correct structure of heteroskedasticity. If the heteroskedasticity function hx is not correctly specified, there are three consequences. First, the weighted least squares, or the feasible generalized least squares estimators, are still consistent estimators of the population parameters, as long as the zero conditional mean assumption or the zero correlation assumption is satisfied for the original model. We can see it from the transformed model. The transformed error term equals the original error term multiplied by the weight. The weight equals 1 divided by the square root of the heteroskedasticity function hx. Similarly, the transformed explanatory variable equals the original explanatory variable multiplied by the weight. The transformed error term must be uncorrelated with the transformed explanatory variable, given that the original model satisfies the zero conditional mean assumption. The weighted least squares estimators or the feasible generalized least squares estimators are the WLS estimators from the transformed model. Therefore, they are consistent estimators. The conclusion does not change whether or not the heteroskedasticity function hx is correctly specified. Since both WLS and FGLS estimators are consistent under the zero conditional mean assumption or the zero correlation assumption, a large difference between the WLS and the FGLS estimates implies failure of the assumption, that is, a misspecification of the model. It is probably due to omitting relevant variables. We should reconsider the choice of the explanatory variables and the model's functional form in this case. Second, if the heteroskedasticity function hx is misspecified, the usual WLS or FGLS standard errors based on the h function will be invalid. So will any test statistics computed using those standard errors. If the structure of the error variance is not correctly specified, the transformed error term will not have a constant variance. As a result, the statistical inference will no longer be valid. Fortunately, there is an easy solution. We can use the heteroskedasticity robust standard errors. Even if the transformed error term in FGLS or WLS may not be homoskedastic, we can still use standard errors that are robust to heteroskedasticity of an unknown form, just as in the case for OLS. Third, there's no guarantee that WLS or FGLS is more efficient than OLS if the heteroskedasticity function is misspecified. We know that WLS or FGLS estimators have smaller variances than OLS estimators if the weights are correctly computed. Otherwise, we cannot rank OLS and WLS in terms of variances. However, in practice, we usually obtain smaller variances or standard errors for the WLS or FGLS estimators than the OLS estimators. We use the workers' hourly wage model as an example to compare the FGLS estimates with the OLS estimates. We are familiar with this model. It relates hourly wages to education, gender, and marital status. We first estimate the model using the OLS method. The BP test for heteroskedasticity gives a large LM statistic and a zero p-value. It is strong evidence of heteroskedasticity. We can employ the heteroskedasticity robust standard errors so that the test statistics are valid. To do that, we add an option of robust in Stata. Or we can use the feasible GLS to address heteroskedasticity. We follow the 4 steps we have discussed in the previous topic to obtain the feasible GLS estimates manually. Stata also provides the head regress command to estimate the model with feasible GLS. Since we are not sure of the form of the heteroskedasticity function, we can use the robust standard errors in the FGLS estimation. I list the estimates from those 4 model specifications. If the zero correlation assumption is met, that is, the error term in the model is not correlated with the explanatory variables in the model, then OLS and FGLS estimates are consistent. The estimates from these 4 specifications should all be consistent estimates of the population parameters. The BP test suggests strong heteroskedasticity. The robust OLS, the usual FGLS, and the robust FGLS are preferred. In terms of standard errors, the feasible GLS has smaller standard errors than the OLS. If the exponential form of the heteroskedasticity function is misspecified, the robust FGLS estimators are the most reliable estimators. Today, we examined the consequences of misspecifying heteroskedasticity and discussed some remedies. Although we will never know the exact form of the heteroskedasticity function, choosing the robust option or using the feasible GLS estimation method usually gives the best results. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.